inviting me to speak. In honor of the organizers, I proposed also a subtitle, The Cliff, the Plateau, and the Waterfall. The cliff, the plateau, and the waterfall. I will explain in a moment what I mean with that. So the focus of this talk would be 4 dimensions and effective field theories. So theories which are looked at in a small regime of energy, in which you can think that this effective field theory is valid at low energy, below some cutoff, which I will call lambda, but you can think of it as being 1 in some units. And the idea is that I will discuss things within this regime, and assuming that I don't know very much about what happens below this heavy scale. Okay, so basically the argument that I want to make is studying the 2-to-2 scattering amplitude. I will limit my arguments to a scalar that I will call pi, and within the effective field theory of pions, the low energy amplitude can take very different forms. In particular, you can have if you are talking about a weakly coupled scalar pi associated with some marginal operator like lambda pi to the 4, the amplitude more or less is constant with energy up to some quantum rounding that I will describe later. But instead, for the theory of pions, where you have an associated scale, the amplitude can grow with energy. And what I want to discuss in this talk is to understand better how this behavior with energy can take place. And the motivation is that if you have something that increases with energy, like the square, or if you have something that increases with the energy much faster, the one increasing faster, like e to the 4 or e to the 8, at low energy is like better hidden, just because it's associated with operators which are more irrelevant, and so you don't see them so much at small energy. And here you have a more phenomenological motivation to study these models, which is the one of understanding what lies, for instance, beyond the standard model or beyond the type of physics that we are testing in experiments today. If what lies beyond is very soft, then it will be harder to see it, just because at low energy, where we perform some experiment, it will be better hidden. Also, if you have something which is associated with an amplitude that runs negative, for instance, it can run positive and then go negative, when it's negative, it might interfere negatively with the marginal operators. And again, it will appear in your cross-section as something which is harder to see, just because the negative interference cancels some of the events. So the idea is that things which are super soft, like that increase very fast with energy, super soft, or things which are negative, amplitudes which are negatives, are somehow harder to see in experiments. And has the motivation of understanding if it's really possible for an amplitude to run negative, and if it's really possible for an amplitude to run very fast with the energy. Yeah, and basically the faster growing would be the cliff, the one falling under the 0 line would be the waterfall, and the plateau I might or might not mention it later. So from an effective field theory point of view, a Lagrangian point of view, all these behaviors are actually allowed. In fact, a theory of pions, the free theory of pions, just the kinetic term, has an infinite amount of symmetry, and in particular, you can shift your pion by any function of x. As long as f is an harmonic function, right? this is a pretty trivial statement, but as long as f is an harmonic function, this type of shift is a symmetry of your Lagrangian, right? And in this form is almost too generic to actually be of any use, but taking different f's will show you, you can label these symmetries and their different effects. So if you take f being a constant, your pion is just a linear shift symmetry. This is the shift symmetry that you have, for instance, for a U1 Goldstone boson at low energy. And your Lagrangian will look like the kinetic term plus an interaction term, which will be d pi to the 4, okay? And the amplitude related with this Lagrangian would be, well, let me just call it A, will go like energy to the 4, okay? On the other hand, if you take a more complicated f with some x dependence, so still an harmonic function, for instance, c plus b times x, your pion now will have a shift symmetry in order to comply with this thing. I mean, it's just, well, it's trivial, it's just that one. But your Lagrangian now will look like d pi to the 4, for instance. There are other terms, but let me not mention. And the behavior of this Lagrangian is much softer. It goes like e to the 8 now. So you see that from a Lagrangian point of view, you can identify the symmetries, and therefore you can justify why the amplitude could be softer and softer. So it could increase faster and faster with the energy. I will refer to the ones that grow too fast, like bigger than e to the 8, as a super soft, as I said before. And now, the symmetries, they don't really need to be exact, right? In principle, you can violate them by a small effect, but still they serve the purpose of giving you like a structural reason why the coefficients in your effective field theory can be organized hierarchically. For instance, let me just look at the amplitude or a tree level associated with some Lagrangian. Let me just write it roughly in terms of the energy. You can have terms that grow with the energy square, terms that grow with the energy to the 4, etc. Right? And the coefficients here, thanks to this symmetry, you can think of this one as being much smaller than this one. You can have, sorry, because of this symmetry. So you can think of symmetry as not something that doesn't need to necessarily to be exact, but just a rationale to organize the various coefficients in your effective field theory. And the type of pictures that you get from this, if the symmetry is not exact, let me repeat them. You can have an amplitude, for instance, that at small energy is characterized by a constant piece, and at high energy, instead, it starts going like e to the 4. And the symmetry associated with e to the 4, so this one is not exact because it's violated by a small marginal operator. So overall, the amplitude goes like this. And in the regime above a certain energy, you really see the Goldstone nature of your amplitude popping out, while when you go to smaller energy, you start seeing the perturbation, okay? And so the question I want to ask now is whether it's possible to have something like this that grows very fast, even if it's, in general. The tool that I will use is that of dispersion relations. That allow me to relate the behavior at small energy of the amplitude with the behavior at high energies. And here I will try to make some very basic but generic assumptions and and use the dispersion relation to relate small energies with this generic assumption. So let me start with the case of the forward amplitude. So the amplitude is a function of the Mandelstam variables S and T for 2-to-2 scatterings, and I will start by looking the limit T going to 0, so just forward scattering. I will consider the object amplitude of S, 0 divided by some powers of S, which I call S n plus 1, and look at the complex S plane this is the real part, there's the imaginary part, and study this object in this plane. So by analyticity, this object is analytic in the whole plane up to some cuts, and I will divide these cuts into two classes. One is some cuts which lie above the scale associated with my effective field theory, this lambda. So these cuts can be thought as coming from heavy particles that I don't know about them. So up here, everything is unknown. And in addition to this, you have some infrared cuts, which are just associated with something that in principle is calculable within the effective field theory. So in this plane, you can think of the effective field theory as being valid within a certain, not well-defined circle around the origin. So this is the circle in which I'm actually trusting my effective field theory expansion, while above here, it's something where I don't know. But I will make certain assumptions about the behavior of the amplitude in the region where I don't know much. And in particular, I will assume unitarity. Unitarity in this picture means that you can, via the optical theorem, you can relate the discontinuity on this branch cut with the total cross-section for the scattering of these particles. And I will also assume a certain form of locality that basically enables me to identify the behavior of the amplitude as S goes to infinity. And in particular, the amplitude under locality goes down faster than a certain function of S. And because of this, the object that I'm considering, the amplitude divided by some powers of S, goes to 0. A divided by n plus 1 goes to 0 for n bigger than 2. Okay? Good. Now, this is something which is more or less well known, but the difference that I will propose now is normally what is being done here is that people look at the amplitude in the origin. On the other hand, the object that I would like to introduce is the arc. The arc is the integral along a certain arc with radius S bar. And this S bar is an energy square that lies within the regime of validity of my effective field theory by construction. Okay? So S bar must be smaller than whatever scale I can think associated with this effective field theory. So in here, I can actually use an ansatz given by my effective field theory, and it's calculable. But because of analyticity and this other assumption, you can deform this contour, and it becomes equivalent to the integral along these two lines parallel to the real line and the big contour. We said that the big contour is sent to 0 because of locality. So basically, the arc becomes equivalent to those lines. Let me write this arc explicitly. Yeah, it's the Flusser bound.
Why n bigger than 2?
So if you divide by n bigger than 2, then this thing goes to yeah. When you do the integral, yeah, exactly. You're right. Sorry, the integral. Yeah. So the arc is defined as 1 over I pi. Yeah, I'm using this sort of curly arc for the arc, and A remains the amplitude. And because of this analyticity, this is equal to the integral from this S bar. Yeah, and by crossing symmetry, this one can be related eventually to the one on the other side. So you can write this as twice the integral from S bar to infinity of the imaginary part of the amplitude divided by Sn plus 1. Good. Let me study some properties now of this object. In particular, I can rewrite this just in this more compact form. I've just pulled out, well, and introduced 1 as S bar to the n divided by S bar to the n. But written in this form, you see immediately that this thing is always smaller than 1, just because the integral runs from S bar to infinity. This is S bar over S, so this is always smaller than 1. Now, because of unitarity, the imaginary part of the amplitude can be related with the total cross-section. And so this thing, the integrand, is always positive. Okay? So from this expression, we can deduce some properties of the arcs. The first one is that for all n's, the arc is strictly positive. That's because the integrand is positive, and etc. So it's not 0, but always strictly positive for interacting theories. The second property has to do with the fact that this thing is always smaller. So if I take a larger power of n, now the integral will be smaller. And so the larger the n in your arc, the larger the integral will be. Sorry?
How did you get the imaginary part? Isn't usually the contour on the other side?
Yeah, exactly. Normally you have the one below, but here by crossing, you can relate it to the one. Sorry, yeah, by crossing you can relate it to the part here, and then by complex conjugation you can go back up to this one. So eventually you get also the imaginary part here. I mean, you can also take the same copy. Here we're assuming anyway that the amplitude up and down is the same. So you, in principle, you instead of the arc, you could also take the sum of the two arcs. So perhaps that would be more intuitive too. Yeah.
With that assumption, you're assuming just one species of pion.
Yeah, here I'm just assuming one pion. Yeah, I'm not. I don't have a charge pion. Sorry. Yeah, only one scalar, single flavor. And
you have ICTP or something like that. Then
yeah. So exactly. No, you can extend these arguments to more complex cases, but here I just wanted to do the single flavor case. Okay. So we have this expression. In addition, since the arc is an integral of something positive, the derivative of this arc with respect to the radius is negative, just because if you take a larger radius, you're integrating less over a positive quantity, so the thing actually decreases. And okay, for the moment, I think I'll stop here. Okay, these are three important properties of these arcs, right? For the moment, they seem uncorrelated with the question that I was posing, but let me now show you how this tool can be used to answer the softmax question. Okay, so the first application that I want to discuss is I will make an ansatz at tree level, just for simplicity. And again, I will focus on the forward limit. We can discuss later some non-forward. Now everything has been in the forward limit, but it can be extended beyond this. Okay, so I assume that my amplitude within, sorry, I remember I had this car lambda. So within this radius, right, where I'm studying my amplitude, I assume that the amplitude can just be written as the sum of some coefficients times powers of n. The amplitude in general is a function of STU and S squared plus T squared plus U squared. And so in the forward limit, STU goes to 0, and it's a function only of even powers of S. So this is C2 S squared plus C4 S to the 4 plus C6 S to the 6, etc. Okay? So the answer that I want to answer, the question that I want to answer, as posed before, is whether is it possible to have C4 much bigger than C2. Is it possible or not? Good. Let me take let me compute explicitly the arcs using their original expression with these ansatz, because remember that the arc is taken with a radius S bar within the effective field theory, so I can just compute it explicitly. And well, here you can think of C2s and C4 as being dimensionful parameters. So yeah, there is no need. But
within the effective theory, the second term is bigger than the first.
Yeah. This is exactly. Sorry. You're good. Sorry, you're right. Yeah. Sorry. It's in units of S bar squared. This would be sorry. Good. Yeah. Let me. Okay. So C4 S squared. Yeah. Let me write it in yellow and big and here. So C4 times S bar squared bigger than C2. Okay. This is the question. Thanks for pointing. Sorry? No, these are the arcs are a function of S bar, right? Now I want to understand whether it is possible for the more irrelevant term associated to C4 to dominate over the one associated to C2 at any scale. S bar, I take it, but you can, this is a more general state. I just want at any scale, is it possible to have this condition fulfilled? Within the effective field theory. So this would be a situation, let me write it again here. So we have the effective field theory. We have some coefficient C2 that goes up square. Let me do it a bit smaller. Right? This would be C2 times S square. And then I have a big C4 in certain units that C4 times S to the 4. And the question is whether it is possible to have a regime within the effective field theory where the effect of the S to the 4 terms dominate. And you can see that for this to be true, you need to have an energy S square equal to C2 over C4, right? You want this to be smaller than the cutoff, okay? So the existence of this regime is the question that I'm after. Does this regime exist within the effective field theory or not? Okay, so I invoke the arcs. And the arcs, with these ansatz, they are very simple. AN is just equal to Cn. And in particular, these have to be positive. Okay, this is already the result that Ricardo, Sergei, Nima, and Nicolis and Adams found in 2006. So positivity of all the coefficients of this expansion. And this is what is telling me that basically these symmetries can never be exact, right? Because if C2, this is for n bigger than 2, if C2 has to be positive, it means that you cannot have a symmetry that kills all the terms up to the one to C4, right? C2 always has to be there, but that doesn't, I mean, you can still have the smaller term C2 being smaller, just a small perturbation that is visible only at small energy. This is the picture that you have here, right? Something small that becomes interesting only at small energies, what the actual big guy, C4, at the beginning is small because it's related to an irrelevant operator, and then it blows up because it's bigger. Okay, so that was the first, using the first condition. Now I can use the second condition on these arcs. And given this expression, this tells me that Cn, or generally, Cn is bigger than S. Cn for n bigger than n. Or for the case that we are discussing there, 2 and 4, C2 is bigger than S squared C4. Ah, surprise, that's exactly the opposite that I wanted to discuss. So basically, positivity of the arc tells me that it is never possible to have a regime in which the super soft effects dominate. Okay? So basically, positivity of the arcs tell me that you can interpret this as just providing you a new cutoff of the theory, S squared smaller than C2 over C4. So positivity of the arcs is basically telling me that this cutoff goes back all the way down to here. And this regime is impossible. So what you started with as a small perturbation, C2S squared, was something that you started with assuming it was small, just relevant at very small energy because it had the lack of being associated with a more relevant operator. It's not really a perturbation. It's a perturbation that dominates all over the regime of validity of the effective field theory. Okay? So, yeah. Basically, the picture that you get from this is that C2 is arbitrary just because is the first coefficient that you can study because of the Froissart bound, but all the next guys, C4, C6, C8, whatever, they will always be subdominant compared to C2. Yeah, never relevant. Let me not use the word relevant. Never phenomenologically important. Never important. Okay. Good. So far I've discussed only things at 3 level. Let me see how this logic is modified at loop level. Yeah, in this thing, it would be less than. It's actually, I mean, assuming the 3-level thing here, I'm basically removing the infrared cut here, right? So yeah, the arcs, they don't care. Yeah, exactly. You can shrink them to 0, and that's when you see easily that the arc is just Cn because it's half the residuum around the origin, okay, which is the usual. So somehow, oh, sorry. Yeah. Yes.
This is probably well known, but I'm a little bit worried about the cut ending at s equals 0.
The cut ending, when you go to 0,
Yes.
S0.
I mean, you write an analytic ansatz, but
Yeah, no, in fact, so this ansatz is, you mean the ansatz is incompatible with the cut going to 0? Yeah, it is, it's true. It's an approximation somehow. Taking that ansatz, I've assumed that the importance of this cut is negligible with respect to my arguments. Now I will put an ansatz which instead has the cut all the way to 0 and see how this gets modified. Okay. So that was the cliff and the classical running. Now I will talk about the waterfall and the quantum running. So loop, and again, forward. So as an ansatz for my amplitude now, I will take a U1 Goldstone boson, so that starts with C2s square, constant, and then this one self-consistently with the ansatz start running at higher orders. This Ls is just log of S plus log of minus S. Now I'm taking the massless limit, so it's simpler. And plus S to the 6, C6 plus. There's a one-loop contribution, which is the same form, and then you can have a two-loop contribution with Ls square, and in principle there can be also another piece with some other form, and here you have log S, log minus S. Sorry. Right. There. Well, up to this order, this is what you get. At higher orders, yeah, I don't know.
Yeah, we were thinking under this minor theorem that we will be able to have the developing loops.
Okay, so I can use them.
I think it's true. I think it is. I don't have no quoted specifically, but it's a good question.
Yeah. Yeah, up to this order is also self-consistent because, yeah, I'm just, you can really compute it, and there is no three-loop thing that enters there. So it's really, that's it. Good, so in this, I can now do the same kind of exercise. I assume that within the validity of my effective field theory, this ansatz holds, and I can compute the arcs just within that ring. So the second one is C2 plus S bar square beta 4. Let me truncate it here just because it's a bit, I'm not going to use the rest later, so perhaps, but we can discuss it about that. The one. And the last one, I'm stopping here, don't worry. Minus. Okay, these are the first three arcs. And then let me also write the derivative of these arcs with respect to S bar. In fact, there is a form which is universal for all of them, divided by the S bar is equal to 3 minus n beta 4. Sorry, about this. Good. Plus order S to the 4. Okay, so, well, the first thing you see is that, of course, at tree level, you match the other answers. You're just recovering. Right, that's a good way of spotting. Sorry. Nothing. I was looking. That's the problem of calling A both the arcs and the amplitude. Okay, so at tree level, if you just the betas go to 0, of course you recover the other ansatz. The thing you see here, however, is that at loop level, the coefficients Cn no longer need to be positive. In fact, here, we have other pieces that when you take S to 0, they become bigger and bigger, implying that you cannot, you don't have necessarily positivity constraints on the coefficient of your effective field theory. So before actually understanding the super soft question, let me understand better the effect of these runnings and how can they impact the positivity of these coefficients. So the first things that we see, right, these I can now get rid of.
But these betas are not three parameters, right? They are fixed by directly.
So the betas, I mean, okay, for the U1 Goldstone boson, you can even calculate them. But in principle, this ansatz holds also if the U1 Goldstone boson couples to matter. So we can think of them as free parameters.
But in this theory, it's just function of this.
In this theory, yeah, they are like, the beta 4 is like C2 squared times something. But this ansatz, it doesn't hold just for the U1 Goldstone boson. But if you couple the U1 Goldstone boson to some massless matter, you would have a same ansatz. And the things I'm going to say hold true in that more general case. Okay.
Is it also so speed dependent? You can add finite parts to the common terms to shift the common terms?
You mean what? Yeah, you mean just putting out a piece from. Yeah, in that sense, yes. Yeah.
Here you made a choice. The argument of the log is S over some.
Yeah, it's S over mu, and here these guys also depend on mu in that sense.
You made a particular choice.
Yeah. No, you cannot. Yeah, you can still think of these guys as depending on mu, and these being.
There's no finite part in the log.
No, then yeah. Sorry, yeah. Okay, so the first thing that we see is that these arcs have to be positive at all values of S bar, right? So here you can take S bar to 0, and you find that at least the first coefficient has to be positive. Good. That's more or less obvious. This expression, remember, had to be negative because it was the derivative of things. Again, we can get rid of the 4 factor. You can take it at very small s, and you're dominated by beta 4. And from this, you find also that the first coefficient is always negative. So the first running coefficient always runs towards more positive values because of the beta 4 coefficient. So if it starts with, if in the UV it has some value, then it will always run to more positive things. And right, this, by the way, is a statement that is not really dependent on my assumption about the Frossard bound and the UV behavior of the amplitude. This is something completely infrared. So this statement, it's in that sense more general. It would be valid also for dimension 5 operators running into dimension 6 and so on. Okay, so good. Those are the first 2 things that you can say. Now, the question that I would like to address next is it possible for a coefficient to run negative? And in particular, the coefficient of C4, we can call this combination the running coefficient. Just this is C4 as a function of S bar. And the question is it possible for this C4 of S bar, at some S bar, to just run negative at a scale that I will call S0? Okay? Is this something that can happen. And you see that, right, I should get rid of this one at the bottom. So I can swap this C4 coefficient just by dimensional transmutation into a function of S0 by the requirement that this is equal to 0, right? So C4 is equal to minus 2b for 1 log of S0, okay? And now, if this thing has to happen, right, if this thing runs to 0 and then even negative, in order to maintain the arc to be positive, you need to be rescued by these guys. But these guys, they cannot be arbitrarily large, because you see that their value is bound to be smaller than 0 by these other constraints. And in particular, at one loop, you can see that very easy, that just this one implies that beta 6 prime has to be negative, so it seems it will not be able to rescue you from this negativity. Anyway, let me go on and just write the full expression. Now, this arc A4, written in terms of this transmuted C4, etc., this has to be bigger than 0. But I can write it as, B for 1. Sorry. I can use this expression, which is always smaller than 0, to see that the arc is always smaller than minus beta 4 times 1. Where this kappa is just the ratio between the 2-loop and the 1-loop coefficients. It's yeah, I've called a combination of these two. I call it beta 6-2. It's just the sum of these, I think, with a factor of 4. But it's not so important. So this is the ratio of 2 versus 1 loop, okay? So in a perturbative context, this would be small. Right, so, well, this function is very simple. I can plot it, and in particular, it has 3 regimes. When kappa is smaller than minus 1/2, this thing is just a function like this. Here we have S bar, and here this is S0 here at the origin, and this is this A4, okay? And sorry, no, it's correct. Beta 6 prime. Yeah. No, what was your question? Beta 4 in front, but this is always negative, so this thing is always positive. Okay. So we have 3 regimes. This is the first. And you see that the arc has to be smaller than this thing. So it pushes you to be below this curve. But you want this to be positive. So you need to be above that curve. And this tells you that you have to be in a regime smaller than S0. So it's just telling you that you're never running negative, because S has to be smaller than S0. So this tells you that your initial hypothesis that the coefficient would run negative is never realized. There's a second regime, which is k bigger than minus 1/2, smaller than 1/2e squared. Okay, where the same things, the curve shifts a little bit up, and it behaves like this. Again, you have to be below the curve, above the horizontal axis, and this singles out this little triangle here, or below. And in particular, it singles out a scale, which is more or less S0 times square root of E1 plus K S0 square. E plus order K S0 square, okay, square. So basically, in order for my initial hypothesis to be realized, that the thing ran negative, now S has to be smaller than this thing. So this implies that if the thing runs negative, the theory gets a cutoff which is parametrically close to S0. So when it runs negative, then pam, I will hit the cutoff very soon. And there is a final regime which is just always positive, but this kappa has to be bigger than 1 over 2 e squared. And I'll just be quick because I'm running out of time. Kappa somehow encodes the notion of a scale, because if you calculate it explicitly, for instance, in the U1 Goldstone boson case, kappa is of order C2 divided by 4 pi square, something like this. And this is of the order, the strong coupling scale of the theory to the -4. So asking that this, the kappa be bigger than this is like asking that the strong coupling scale becomes smaller and smaller. So again, you have a notion of a cutoff that gets closer and closer to your parameter S0. So basically, the answer of this part is that if my coefficients run negative, then my theory gets a lower cutoff, parametrically close to the scale in which my coefficients run negative. Right, since I'm out of time, I'll just summarize some other results that you can get from this analysis. Sorry? Oops. Yeah?
I'm confused a little bit.
Yeah.
Why did the series start at S squared?
S squared, yeah. Why? So it's a U1 Goldstone, so you're right. There could be a term which is C0. It's constant. That could be there. I just, and
We're worried about terms with
S. No, S is always vanishing because the amplitude needs to be a function of STU and S squared plus T squared plus U squared.
Identical part.
And
Identical part.
yeah, it's only one pion. So
Identical scalar.
for identical scalar, the amplitude can only be a function of these things. And in the forward limit, the odd powers goes to 0. And so you're left only with even powers.
You make scattering of charge ions.
No, then you have S. You're right.
Only pi 0. This is pi 0, pi 0.
Yeah, no, for
Pi 0,
yeah, it's pi 0 scattering. Okay, yeah, sorry for. Okay, so let me just summarize the remaining things. Okay, so one of the remaining things is that this argument that I showed to you at tree level, you can show that at loop level becomes always stronger. So you always have like C2 bigger than C4S squared, and what is it? Plus something which is always, you can show it's positive. So your arguments actually become stronger. So super softness is more constrained at loop level when you have a properly functioning ansatz. Okay, that's one more result that I didn't show. And the other one is that actually you can extend this thing in the regime of t different from 0, in particular in the non-physical region of t bigger than 0 and smaller than 4m squared for a massive particle. You can show that also that the amplitude in this regime is also has the same properties as the forward amplitude. And in this case, you can make also exclude the super softness for amplitudes that vanish in the forward limit. So for instance, an amplitude which goes like STU times S squared plus T squared plus U squared, right? You can show that this can never dominate your amplitude, okay? Good, just. This is now massive, yeah. It needs to be massive in order for this regime to be.
But you're still expanding around that.
Small mass, yeah. Eventually, I take derivatives in 0, so the mass can be arbitrarily small, just present. Yeah, expand the thing in 0. I can show this better offline. It's actually quite interesting because you don't have positivity. You have basically your object, your arc now is a function of t, but you cannot use it in its whole because it will be always dominated by the t equals 0 piece, which we already studied. So you need to expand in powers of t, and T and U channel give positive and negative contributions. So you don't have something which is manifestly positive, but you can arrange for some combinations to be positive. And you find constraints which are similar to the one that I posed you before. So yeah, in summary, basically, this idea of super softness, which I introduced at the beginning, it's gone by the end of the talk. And the cliff, it cannot be realized. And this is true both in the forward, for amplitudes that both vanish or not in the forward limit. In particular, you see from this that coefficients, the C0 or C2, these are arbitrary. Well, this has to be bigger than 0, but the coefficient C4 and higher, they cannot be realized. And similarly, for things that vanish in the forward limit, you find a similar hierarchy in which the first one, the coefficient of STU, is arbitrary, but the other ones cannot be there. And at loop level, yeah, there is this nice story that you think things would be able to run negative, but in fact, it doesn't work. Well, it does work, but it's very short, the amount of negativity they can have. And I think that's it for now. Thank you very much. Yes?
So you have some non-perturbative statement about these arc functions.
Yeah.
And then you're trying to say statements in perturbation theory, so like a tree level of one.
Yeah, exactly.
And so for that to work, your perturbation theory has to be valid. You can ask, when is the loop as big as the tree level?
Yeah.
And
Well,
that's exactly the condition that A2, so you have this expression C2 plus beta 4, or you know, C4 plus beta log, right?
So yeah.
when the tree level C4 is the same as the loop is when it can go negative, and that's what perturbation theory is breaking down. And you concluded that in fact the cutoff is going down, so perturbation theory is breaking down. So it seems that you're just concluding the sort of obvious thing that your perturbative expansion breaks down when the perturbative expansion breaks down.
Well, this is an ansatz which is not necessarily perturbative. I mean, this is complete at all orders in up to these powers of energy, because I can only have my s to the 4, right? Can only get contribution self-consistently only at one loop, and here you would have this singularity appearing. So this ansatz pretends to be non-perturbative in that sense. It's perturbative in the energy expansion, but it's not perturbative in the coupling expansion.
What breaks down, but you're right. What you're saying is...
Yeah, heuristically, it's
the derivative expansion.
But it could have been that C2 is accidentally small if the efficiency doesn't break down. Like if we exclude that possibility, so it could be the first correction larger than the zeroth order, but second correction is smaller than the first, and perturbation theory works. So
yeah, that was the point, yeah.
Essentially, the derivative expansion breaks down. So the effective theory, which is based on the derivative expansion, is going to get 10.
Let me think about it.
But yeah, I think in a sense it's kind of obvious, but you can simplify it. You want to make sure that it's obvious. It's not.
Somehow it's as obvious as the first three-level statement, right? That C2 has to be bigger than C4 times S squared, right? When you look at this, you say, oh, of course, this is like just that the next term has to be smaller than the first one, which ordinarily that's what happens. But as I argued, structurally with symmetries, you can actually have this much smaller in principle. So it's true in ordinary theory, this is always realized.
You're not concluding that it can't happen. You conclude that if it happens, then your perturbation expansion breaks down.
Yeah, exactly.
Effective theory breaks down. Means that there are new states.
But that's not, you're,
That's what we do. I mean,
oh, go ahead. You're saying it's obvious, or not?
that's the definition of when if it were, I could, without doing any calculations at all, I could say, if it's true that the higher order coefficient is bigger than what you expect, then effective field theory is not.
Well, that's the naive statement, in my opinion, because it's naive, you would say that, right? But then you look at the Lagrangian, and you can find symmetries for which everything is 0 up to order s to the 6, right? And then Lagrangian is completely self-consistent because there is a symmetry, so the lower order guys are not generated. So there is no breaking down of any perturbative expansion. So it's Lagrangian, which from an EFT point of view is completely valid, right? And we show that this is cannot be the case. So I agree that you're like, yeah, first it's obvious, then it's yeah.
Lagrangian guy, it just goes perturbation theory, just goes computation, never will find any consistency. Very much like the original, in the original paper, we said that C2 has to be positive in perturbation theory. And unless you make this assumption about the UV of the theory, when you use the special relation, you could not tell. I mean, C2 negative was a perfect effective theory. You can do perturbation theory, you never realize it. It's not possible.
Yeah.
This is the same thing. This is exactly. So it's obvious. That's why it's interesting. That's why it's interesting. It's obvious.
So here you did the simplest case
It's obvious if you look at it from the right perspective.
with a single particle.
Yes.
But, I mean, several people already asked, if you introduce flavor,
Some flavor, yeah.
more general structure, do you still think that this was going to be a general structure, but you can never have?
I think this would be pretty general. What would happen? Yeah, is that basically your C0, and in that case the C1, this would be still arbitrary because of the Frosser bound, you cannot say anything on these two guys. But starting from this one up, you will have similar constraints. Now, yeah. So that's what I expect. And I expect this because basically somehow the bounds at t different from 0, they address the odd coefficients. So I expect that basically the entire thing goes through in a similar way.
Any other questions? Okay, let's thank Francesco again. And break for
Thanks.